Hey guys, and welcome back to another video on the channel. In today's video we're going to be proving the formula for a Taylor series. So a Taylor series is pretty much you can approximate a function using a pretty much an infinite series. If you know its function, you can work out pretty much the series for it. So for example, if you have y of x, so your function can be represented as the infinite series, so ranging from n equals 0 to infinity. If you know let's say the nth derivative, so this is pretty much this derivative will change depending on its index. So this is pretty much f to the not to the power of. This is just the derivative of x of 0. So x of 0 is where you pretty much start up your approximation from. So it can be pretty much any point on n factorial multiplied by x minus x naught n factorial. So this x naught pretty much says where you want to start your approximation from. So most of the time x naught is equal to 0, so they like to start the approximation from the origin pretty much, okay? So to pretty much prove this is an approximation of our function, we need to use pretty much the fundamental theorem of calculus, okay? So if we have, let's say, a smooth function between a certain interval, so let's just say we have f of x, and let's say it's smooth between the intervals, so let's say f between the interval of a and b, you get pretty much real numbers throughout the entire output. So pretty much there's no singularities between those intervals, okay? Well, you pretty much know if we integrate our function f of x, you're going to get another function with some constant, so capital F of x plus c, which is pretty much your area function, okay? Now, if it is continuous on this interval for f of x, if you integrate it, that means capital F of x also must be continuous. So that means capital F pretty much along this same interval will produce real numbers. So that's pretty much what this is saying here. Between these two values, including a and b, you'll get real numbers, okay? So if you include bounds on an integral, that means you go from a to b of f of x, pretty much you're going to get f of x, but with a capital F, a and b, and you substitute the b and then you subtract the a. So what you get is f of b minus f of a, and it's still equal to this integral here, pretty much, okay? So you get this following expression. So this is pretty much the fundamental theorem of calculus, okay? Now you can rearrange this. So you pretty much get this following bit by itself. Because if you move the f of a to the other side, because if you move it to the other side, you get it by itself. So you get plus f of a on both sides. And you get an expression like this. So you get f, capital F of b, is equal to f of a plus the integral from a to b of f of x dx. Now, b, this number here, doesn't have to be fixed. It can represent some other variable in this case here. So let's just say it's equal to pretty much t. So b isn't fixed. So let's go b equals t, okay? So what we get is this following expression. So capital F of t is equal to f of a plus the integral of a to t of f of x dx, okay? Now, because we know the integral of f of x dx is equal to capital F of x plus c, that means f of x must be f, capital F dash of x, so the derivative of f of x, this one here, okay? So if we were to substitute this into here, what we get is this following expression now. We get f of t equals f of a plus the integral from a to t of capital F dash of x dx, okay? Now, what we can do pretty much here is we can apply pretty much what we just did there for, so know how we did it for f of x here, we can actually do that for f dash of x as well, okay? So if we were to think of this in another way, if we have, let's say, let's go f double dash of x, and you were to integrate between a and b, what you're going to get is f dash of b minus f dash of a. Now, rearranging it like we just did up here with t's and stuff, what we're going to get is pretty much f dash of x is the same as f dash of a plus the integral from a to, let's go x, but instead of t, because we've already used it, we have to do t1, so it'll be f double dash of t1 dt1. Okay, now let's get rid of this, and we're going to pretty much combine these two somehow. Okay, so we've almost got a way so we can plug this into here. We just need to pretty much get an expression like this. Okay, so to get this green bit here, we have to integrate this side from a to b, from a to t with respect to x. So we need a dx there. Okay, so if I just move that to the side, I put a dx there. Now what you do to one side, you have to do to everything. So if I integrate this whole side, so what I've just done there is I've made that the green bit there. But I now have to integrate everything here. So that means I pretty much need to split this up very quickly. I need to integrate each of the terms along the same bound. So I added this here. So I need to add that to everything now. So it'll be the integral from a to t dx, and then the same thing here. Now even though there's an integral here, you can make that a double integral. So what we're going to do is pretty much have that integral on the outside. So we'll have the integral from a to t, and then we'll attach the dx on the outside. So what we can do now is we can pretty much substitute this entire bit into the following expression above. Okay, so what we'll get pretty much if we do that is we're going to get capital F of t, so f of t equals f of a plus the integral of a to t f dash of a dx plus the integral of a t, the integral of a to x, f double dash of t1 dt1 dx. Okay, now we can actually work out what this bit is straight away. Now this here, since this was a function, this is pretty much the derivative of capital F, but we've plugged in a value. So this entire thing here is a constant, so it's independent of x. So what we can actually do here is we can actually factor that out of the integral. So if I move this to the side, we can actually take that out of the integral itself. So all you have is the integral from a to t multiplied by dx. Okay, so that's independent. Now if we work out what this is, the integral of 1 would just be that whatever that variable is. So what we pretty much have is just x with the bounds a and t. Now if you plug that in, what you're going to get is just t minus a. So this blue bit here turns into just t minus a. So you can replace that there. Okay, so you get multiplied by t minus a. Okay, now we want to try and evaluate this double integral at the back pretty much. Okay, so applying the fundamental theorem of calculus pretty much to this guy here, we can rewrite, alright, f double dash of t1 is the same as f double dash of a plus the integral from a to t, now we have to do t1 because we've already used that, so t1 of our third derivative now, so our third derivative with a new variable, let's go t2 dt2. Okay, now if we want to pretty much make this equal to our double integral here, we need to attach the double integral. So that means we have to integrate here and here, so we have to attach both of those. So you get a to t and a to x, and you have to do that to everything here. So you get a t x, and you get a triple integral in the end. So if we attach that integral now, we also got to include those bound bits on the end here. So this would be what would that be? That would be dt1, yep, dt1 and dx, dt1 and dx, double integral a tx, dt1 and dx. Okay, if we evaluate whatever this is, we know that f double dash of a is also a constant, so it's independent of both of the integrals here. Okay, so this blue bit, once you work out whatever that integral is, it actually turns straight up into f double dash of a times by a half of t minus a all squared. So that is pretty much that blue bit there. Okay, so if we were to pretty much plug this entire thing here into here, what we're going to get is this following expression. So we get f of t equals f dash of a and t minus a plus f double dash of a on 2 times by t minus a squared plus this triple integral here. Okay, so a to t, a to x, and then a to t1, the third derivative in here of t2, dt2, dt1, and then dx. Okay, now if you keep doing this pattern that what we're doing, what we're going to get is a following pattern like this. We'll get f of t equals f dash of a multiplied by t minus a plus f double dash of a on 2 multiplied by t minus a squared plus the third derivative, so f of 3 up here, a on, what would that be? That'd be, what's it called? 6 on t minus a to the power of 3. And if you keep doing this on, what we're getting is a pattern like this. Now, what we actually have here, this is 1 factorial. This here is 2 factorial. And 6 is another way to write. So 6 is the same as 3 times by 2 times by 1, which is 3 factorial. Okay, so what we actually have here is 3 factorial. So if you did that indefinitely, this here is the exact same as this infinite series. F of t is the same as the infinite series, so the discrete series from n equals 0, so that's your starting index to infinity of, let's go, what would that be, f. So if I go capital F to the nth derivative, a on n factorial on, what would that be, t minus a to the n. Okay, now this is the formula for a Taylor series. So your function is exactly the same as this infinite approximation. Okay, and yeah, that's about it really. I hope you enjoyed this video. If you have any questions, try and leave something in the comments and I'll try my best to explain it, okay? But in the meantime, I'll see you in the next video.